The cosmic speed limit, the speed of light in a vacuum, is absolute for objects moving through spacetime. However, general relativity permits the manipulation of spacetime itself. Miguel Alcubierre proposed a mechanism in 1994 that allows a spacecraft to travel effectively faster than light without violating local physics. This concept, the Alcubierre Drive, relies on creating a localized distortion field, often called a warp bubble. Inside this bubble, the ship remains stationary relative to its local environment. The key is that the ship is not moving. The space around it is contracting in front and expanding behind. This differential manipulation of the metric tensor allows for superluminal travel relative to distant observers, maintaining the integrity of special relativity within the bubble. The Alcubierre metric is a specific solution to the Einstein field equations. It describes a spacetime geometry where a region can move arbitrarily fast relative to flat spacetime. The metric tensor, g mu nu, defines the geometry, incorporating a shape function f of r sub s that dictates the size and velocity of the warp bubble. This function smoothly transitions from the flat spacetime outside the bubble to the highly distorted region inside. Crucially, the metric ensures that within the bubble, the ship's forward velocity remains time-like, meaning the ship experiences no relativistic effects like time dilation or length contraction. The drive achieves its effect by shifting the coordinate velocity of the bubble, v sub s of t, which can exceed the speed of light c, while the local velocity of the ship remains zero. The warp bubble operates by dynamically altering the spatial components of the metric. Ahead of the spacecraft, spacetime is compressed, effectively shortening the distance to the destination. Simultaneously, behind the spacecraft, spacetime is expanded, increasing the distance from the origin. The ship rides the resulting wave of distortion. Imagine standing on a moving escalator. You are stationary relative to the step, but the escalator moves you quickly across the floor. The Alcubierre Drive is analogous, using the expansion and contraction of the universe itself, but localized and controlled. This mechanism avoids the infinite energy requirement associated with accelerating mass to light speed, as the ship itself never accelerates locally. Implementing the Alcubierre metric requires a specific distribution of energy and momentum defined by the stress-energy tensor T mu nu. Calculations show that the drive necessitates regions of negative energy density, violating the standard weak, strong, and dominant energy conditions of classical physics. This hypothetical substance is often termed exotic matter. Negative energy density is required to generate the repulsive gravitational effects needed for spacetime expansion behind the ship. While negative energy is theoretically possible in quantum field theory, specifically through effects like the Casimir effect, generating and sustaining the vast quantities required for macroscopic warp travel remains the primary physical hurdle. Initial calculations suggested the energy requirement for a small warp bubble was equivalent to the mass energy of Jupiter. Subsequent theoretical refinements, particularly by Harold White, proposed modifications to the shape function, potentially reducing the required exotic matter to manageable levels, perhaps the mass energy of a Voyager-sized probe. These reductions rely on optimizing the bubble geometry into a toroidal shape rather than a sphere. The physical realization of negative energy density is linked to quantum vacuum fluctuations. The Casimir effect demonstrates localized negative energy density between two closely spaced plates, but scaling this phenomenon to power a starship remains speculative and potentially limited by quantum inequalities. Superluminal travel inherently raises concerns about causality violation. If the warp bubble allows travel faster than light relative to distant points, it might permit the creation of closed time-like curves, theoretically enabling time travel into the past. However, the Alcubierre metric itself does not explicitly guarantee the existence of closed time-like curves, depending heavily on the specific path and duration of the superluminal journey. Furthermore, the requirement for exotic matter might intrinsically prevent causality violation. If the laws of physics prohibit the stable creation of exotic matter configurations that lead to paradoxes, then the drive might be physically possible without breaking the fundamental arrow of time. Beyond the exotic matter problem, significant engineering challenges exist. The metric predicts immense tidal forces near the edges of the warp bubble, potentially destroying the ship or its occupants if the shape function is not perfectly smooth. Furthermore, controlling the destination is problematic. Since the ship is causally disconnected from the space outside the bubble, information cannot travel faster than light to guide the ship or stop the drive. Once activated, the ship cannot receive external navigational data until it decelerates. A related issue is the warp field discharge, where particles accumulated in front of the bubble are released upon deceleration, potentially creating a lethal burst of high-energy radiation at the destination.
Research continues into alternative warp metrics that minimize or eliminate the need for exotic matter. The Krasnikov tube, for instance, uses a permanent distortion of spacetime, but requires pre-placement of the tube structure. More recently, physicists have explored metrics that utilize positive energy density, relying on specific configurations of mass and momentum, though these often result in subluminal speeds. The Alcubierre Drive remains a crucial theoretical benchmark because it demonstrates that superluminal travel is mathematically consistent within general relativity, provided the necessary stress-energy conditions can be met. Future breakthroughs in quantum gravity or manipulating vacuum energy are essential for transitioning this concept from theoretical physics to engineering possibility.